Hello. All right. Let's see if we can figure out how to get information about this stream. YouTube.com. There we go. All right. Welcome. See, we've got one other person in. I'm trying to figure out if I can set up the link a little differently from the classroom so that people can see the chat as well as the video feed. If you can hear me, if you could say so in the chat, that would be helpful. Hello, welcome. Great, thank you. That's really helpful. It looks like there's about a 3-second delay between when I say something and when that information gets through the live stream on the app. Set up as a video on top, chat and bottom. Awesome. Thank you, Madeline. That's really helpful to know. I think when you click on the link through Google Classroom, it just shows the video. But if people open it in a new tab or as you're doing on the app, then it should be fine. So if you're just seeing the video and you can't see the chat, try opening the link from the classroom in a new tab, and then hopefully that should work out so that you can see the chat and you can type any questions that you have there. All right, so we've still got a couple of minutes before 11. So for now, we'll just wait, and then once it hits 11, we'll get things started. I'm actually using the document camera here because I don't know how to switch cameras partway through, so we'll adjust it down and get started with the explanations there once we have that option. All right, we've got someone new joining us. Welcome. If you're just seeing this as the video because of the classroom link, if you open the link in a new tab, then you should be able to see the chat as well, and that'll help you if you want to ask a question. All right, I think we are going to get started. Welcome, everybody. Start with a quick explanation of what's up and how things are going to work, and then we'll jump right into the math. So first of all, as usual, welcome. This is day 12 of remote learning. And we have our joke for today is what is the best time to go to the dentist? 2:30. I'm sorry that was such a terrible joke, but hopefully expected. There's a few different documents that are up in the Google Classroom that will accompany today's lesson. I don't have printouts of them, and you won't need printouts either. But I just wanted you to know that they're there because they give you some visuals that help you to follow along. I'd ask that if you're one of the last 2 people in the stream at the very end, if you wouldn't mind staying on. Once we get down to just 1 student in the stream, I have to close the stream down. So if you're the second last or even the third last, if you wouldn't mind just leaving the stream open, that would really help whoever's asking the last question to be able to get an answer to their question. So I think with that, we can jump right in. I am trying to monitor the chat, but I do have to jump back and forth a little bit between the tabs in my browser. So it may take a few seconds for me to see one of your questions. But please, if you do have anything to ask, just type it in the tab or in the chat, pardon me, and I'll see if I can find it there. So with that dealt with, let's get started. Gonna switch this, rotate. There we go. Lamp on. All right. So we'll get rid of that stuff and move into our next piece. So we're going to start with the Trig Toolbox document. So if you can have that open in a separate browser, that's probably, or a separate tab, that's helpful. Some of these Trig identities are identities that you know from last year. We'll start with one of those. Other Trig identities are things that we can establish by our knowledge of transformation. And so if you open Desmos in a tab, that will be helpful as well, because you'll be able to see the transformations and to tell that we are indeed working with identities. Are things loud enough for people to hear? If you could just let me know in the chat if you're able to hear things clearly, and that way I can make sure everything's going well. So the Trig Identity Toolbox, we're going to start with the quotient identities. These are, or this one is one that you learned last year, which is that, hold on, sorry, we need to do more rotation. No, more rotation. Yeah, there, no. This is really weird. It's got it backwards. So this is the left side of the paper, but on the chat or in the video, it's looking like the right side of the paper. I don't seem to be able to rotate that. Okay, thanks folks in the chat for telling me you can hear clearly. I'm going to see if I can figure out what needs to happen here. Rotate. Okay. No. Oh, thanks, Rumaisa. That's really helpful. Okay, I'll see if I can get it rotated back then. And okay, and now the rotate button is not working. Excellent. My apologies that we're doing troubleshooting live here, but hopefully we can get it working. There we go. Okay, so hopefully this is showing up the correct way for you, and I'm the only one who's seeing it weird. So we're going to get started right in. So the tan x or tan theta, and those of you who haven't seen theta, it's just a Greek letter that's used as a variable for an angle. So tan theta equals sine theta over cosine theta is hopefully one that you know from grade 11. So this is the first of the quotient identities, and it's going to be useful to us today. Thanks, Rumaisa. That's helpful to know. So if you look in the toolbox, we have quotient identities. We won't worry about the cotangent one yet because we don't need it today. We also have the parity identities, and these ones are going to be pretty important for us. So first one is sine negative theta. And this one we can actually work out very easily because we know that sine is an odd function, and our definition of an odd function is that f of negative x equals negative f of x, and we're going to apply that definition directly here. So sine of negative theta equals negative sine of theta. And for the cos identity, we're going to make use of the fact that cosine is an even function, And for even functions, f of negative x equals f of x. So that's for even functions. And so we get cos of negative theta equals cos theta. Both of those are going to be very useful for us today. Okay, next one up is sine pi by 2, and pi by 2 is the radian for 90 degrees. So we're going to talk about this in terms of degrees right now. 90 degrees minus theta. So this is our cofunction identity, the first one. What we want here is to think about this in terms of transformations. So in Desmos, and I will pull this up here on my Desmos, and then we'll see what happens when I try and put the screen in front of screen. I'm not sure it'll work super well, so you might have to do it on your own Desmos. Let me just check how that's working. Okay, it looks like it's not super terrible. Okay, so we can see here I've got a graph of cosine of x, and I have a graph of sine of 90 degrees minus x. And you can see that when I turn on or off the graphs, that we're getting the exact same graph. So there's no difference between the two graphs, and therefore these two functions are identical. And so we get the identity cos x, or sine 90 minus x, equals cos x, or sine 90 minus theta equals cos theta. And that's in degrees. If we were to write it in radians, we'd have sine pi by 2 minus theta equals cosine theta. So that gives you a bit of reassurance that these are in fact accurate. It turns out that it's true the other way around. So cosine of pi by 2, or 90 degrees, minus theta equals sine theta. And if you put both of these functions into Desmos, you can prove that for yourself there as well. So that is the main preparation that we need. I'm going to pause for about 10 seconds. If you have any questions, feel free to type them in the chat. You can even just type the word question so that I know that you're writing something longer if you feel like it's going to take you a while to write it. So I'll give you 10 seconds to do that before we move on. And while you're doing that, just a welcome. I see we've had some more people arriving in the chat. If you've clicked on the link through Google Classroom and you can only see the video, you can't see the chat, try opening it in a new tab. If you do that, you should be able to see the live chat, and that's how you'll be able to ask questions. So welcome to all of you who are here. It's pretty nice to finally have a little bit of interaction again, even if it's limited. All right, so it looks like people are good with these identities. We know the tan quotient identity from last year. We know sine of negative theta identity and the cos of negative theta identity just on the basis of our odd and even function knowledge. And we can establish through transformations that sine 90 minus theta is equal to cos theta, and cosine of 90, or pi by 2 in radians, minus theta is equal to sine theta. All right, so we're going to move into our main topic, which is the compound angle formulas. Compound angle is just a fancy way to say an angle that is made up of more than one angle added or subtracted together. So the first one that we're going to look at is for sine, and it's the addition of two angles, and we'll use the Greek letters alpha and beta to represent those angles. And the formula that we're looking for is sine alpha cosine beta, so sine alpha times cosine beta plus sine of beta times cosine of alpha. So that's the formula that we're looking to establish, and that will let us deal with sines of the sum of two different angles. So where can we go with this? How can we prove that this is true? Well, I'm really happy we're doing a live stream lesson because the proof is a little bit complicated, not crazy complicated, but definitely enough that it'll be helpful that people can ask questions. So if you open up the other PDF document, the one called Compound Angle Formulas, you'll see that it has a diagram there, and that diagram is the one I'm going to reproduce on this piece of paper for you. We're going to add a little bit to it as well, but if you want something to give you an idea of what it's supposed to look like a little bit better than my drawings, that might help you out. As well, this whole proof is reproduced in the document called Proof of the Compound Angle Formula. So if you would prefer to follow along there, there's a slightly more detailed diagram that might be helpful to you. So the basic idea, I just want to make sure I'm getting this on camera. Yeah, okay, the basic idea here is if we have an angle, two arms, and we'll call that angle alpha. And then we have, along with alpha, a second angle that is added to it, and we'll call that angle beta. So the question is, if we're looking for the sine of these two angles combined, the sine of this total angle here, how can we find the value of that sine if we know the values of the trig ratios for alpha and beta separately? And so the proof for this, we're going to combine it. We're going to pick a point, any point, doesn't matter which one, on this final arm of beta. And we're going to draw a line straight down 90 degrees to the initial arm of the angle. And to label some things, we'll call those points A and B. We can call this one O for origin. And then we're going to make another line. We're going to go 90 degrees from this line to A. So like that. And we can call this point C. And then from C, we're again going to drop straight down 90 degrees to the original arm, and we'll call that D. And you might say, why are you picking these particular things? I'm picking them because they work out. So with a proof, we often use the method that works to show that something must be true. And so I'm not showing you how people discovered that this works. I'm just showing you the method that they discovered and why it works. All right. So the very last line that we need to draw here is from this point C, we're going to draw a perfectly horizontal line across 90 degrees right there, and we can call that point E. So that's our diagram, and if you look at the Proof of Compound Angles document, you can see that it's basically a reconstruction of that diagram there. All right. Just going to check the chat, make sure there's no questions. Okay. So next up, we're going to start trying to figure out what we can say about sine of alpha plus beta. So sine of alpha plus beta, that's the sine of this whole combined angle here. We're in a right-angled triangle, and so sine is going to be opposite over hypotenuse. And so the opposite here is the side from A to B, and the hypotenuse is the side from the origin O to A. And so that is our ratio. Opposite over hypotenuse is equal to the sine. And so then we're going to just break this down according to some geometry. So the first thing that I notice is that AB is actually made up of two pieces, from A to E and then from E to B. And so I can split AB into the sum of AE plus EB. The distance from here to here is going to be equal to this distance plus this distance. If I add those two together, I get the full length of it. So that's our first step. Leave the denominator to the same. And then we're going to separate this into two fractions. So AE over OA plus EB over OA. All right. So again, I encourage you to ask questions in the chat. This proof is, I wouldn't say the most difficult thing in the course, but it's definitely in the category of some of the more difficult things that we go through in the course. All right. So we've got this split into these two pieces. We're going to make one more observation geometrically before we start into a little bit of algebra. And that observation is that this length from E to B is one side of a rectangle. So we have a rectangle here. You can see we're getting right angles. So this is going to be perfectly rectangular. And as a result, EB and CD are going to have the same lengths. And so instead of using the length of EB, which isn't really part of any triangles, we're going to use the length CD in place of it because that is the same length and it's part of this right-angled triangle involving alpha. So AE over OA, still true, still the same. But instead of EB, we're going to replace that with CD. All right. So again, I'm going to pause, give you a chance to ask any questions that you have. And in a few seconds, we'll move on. All right. So we're going to keep working here. We're going to make a little addition to AE. And that is we are going to multiply this first fraction, AE over OA, by 1. But as we so often do in fractions, we're going to use a kind of tricky 1. And we're going to go AC over itself. And since AC over itself is 1, we're just multiplying this by 1. We're not changing its value, but this is going to be helpful to us later on. And the second part, we have CD over OA. And so we are going to multiply that again by 1, but this time we're going to use OC over itself as our way of writing 1. All right, so a little bit of trickery here, but you can start to see now that we have a ratio times a ratio plus a ratio times a ratio. And if we look at the formula, that's exactly what we're looking for. Trig ratio times trig ratio plus trig ratio times trig ratio. And so we're going to need to do a little bit more playing around before it works out, but we're on the way to what we want. Okay, question from Rumesa. Does this theorem also apply to subtracting angles? An excellent question. We are going to also develop the formula for sine alpha minus beta. We're going to use this theorem to do it. We do technically have a different formula, but I'll be honest with you, I don't actually remember both formulas. I just remember this formula. Go alpha plus negative beta and carry that through using this formula to get the formula for subtracting. So you can get the formula for subtracting very easily from this formula. All right, let's keep working here. So we're just going to make a little switch, OA times AC. So here we're multiplying fractions, which is top times top, bottom times bottom. And since in a multiplication order doesn't matter, we can switch the order. And so that's what we're going to do. We're going to go AE, and we're going to switch the order of OA times AC and make it AC times OA. So we'll have AC here times, on the top we'll leave the order the same. So we've just switched the OA and the AC order. And we're going to do the same thing over here. CD over OA. Oh, sorry, over OC, because we're times OC over OA. And so now we're actually AE over AC, pardon me, is two sides of this triangle, this side and this side. And so if we knew what the measure of this angle was in terms of alpha and beta, then we could say that cosine of this angle is going to equal to the adjacent side divided by the hypotenuse, which is AE divided by AC. So we need to figure out what this angle is. Well, it turns out that's actually pretty easy to do. The first thing we do is we say, okay, this is a rectangle here. So this side and this side of the rectangle are parallel. Since those are two parallel lines, this and this, and we have a line cutting through them, our Z pattern, making a Z here, means that this angle and this angle are the same. So that means this little angle in here is alpha. And again, a little pause, some time to think about it. Do you agree this angle in here has to be alpha because we have parallel lines and a Z pattern? Okay, so once you agree with that piece, now we're going to look at this big angle is 90. This part of it is alpha. So the part that's in this AEC triangle is going to be 90 degrees minus alpha. So I'll write that down over here. So it's going to be 90 degrees minus alpha. So that's this angle in triangle AEC. This angle in triangle AEC is 90. We add them together. If we simplify that, we get 180 degrees minus alpha. Okay, so triangle AEC, these two angles add up to 180 minus alpha. If we add in this last angle, we should just get 180. Because it's a triangle, the angles have to sum to 180. So what does this angle need to be? What do I need to add here to make this into 180? Well, it's 180 minus alpha, so if I add alpha, it's going to cancel and we'll be left with just 180, which is what we know the sum of the angles has to be. So it turns out this missing angle here has to be alpha because that's the only way to get these angles to add up to 180. So if that angle's alpha, then we get 180 minus alpha plus alpha, which is just 180. Okay, pause again for questions. All right. To what we were working on here, now that we know the top angle is alpha, that lets us work in this triangle. So AE over AC is the adjacent side to alpha divided by the hypotenuse. And AE over AC is cosine of alpha. AC over OA, so that's our second ratio here. And in the diagram, that's this side divided by this side. So now we're looking at this big triangle. And for angle beta, AC is the opposite side. OA is the hypotenuse. Opposite over hypotenuse is sine. So this is sine of beta. CD over OC. CD is here, OC is here. So we're looking at this triangle. Again, a right angle triangle. It has alpha in it. CD is the opposite side from alpha. OC is the hypotenuse. So this is going to be opposite over hypotenuse, or sine, for alpha. And then finally, we have OC over OA. So we're working in this triangle now. OC is adjacent to beta. OA is the hypotenuse. Adjacent over hypotenuse means that we have the cosine. And this is the formula. We can change the ordering of things a little bit. So if I bring this term to the front, I'll have sine alpha cos beta plus, and then in this one, I'm going to switch the ordering of the multiplication because that won't change the result. So we'll do sine beta cosine alpha. And there we go. We've arrived at the formula that we were trying to prove from the start. All right. So that's a lot of not super easy to follow math. I'll take some time for questions. If you were able to follow some parts, but not all of this, you don't need to be really worried about that. I'm not going to ask you to ever prove this theorem, but I would like you to have some understanding of where this result comes from and some clue of why it's true. So pause a little bit for questions before we start using this. All right. So we've established our original formula. Rumaisa asked a question about the formula for subtraction. So if we had sine of alpha minus beta, what could we do with that? All right, so new formula here. We've proved what we were proving there. What can we say about sine of alpha minus beta? Well, we can say that that's sine of alpha plus negative beta. And now we can apply the sum formula. So sine of alpha plus negative beta is sine of alpha cosine of negative beta plus sine of negative beta cosine of alpha. And so that's just me using the formula here and applying it with negative beta instead of beta. And then we can go back to those identities that we established at the beginning, the parity identities for odd and even. And so just a reminder, that's this stuff right here, that sine of negative theta is negative sine theta, cosine of negative theta is cosine of theta. And so we can apply those here, sine alpha times cosine. Well, cosine is an even function, so cosine of negative beta is the same as cosine of beta. Sine of negative beta, sine is an odd function, so that's going to be negative sine of beta. Cosine of alpha we can leave as it is. And then finally, there's a subtraction here. Adding a negative is the same as subtracting. And so now we can see that if we have a subtraction, the formula is going to be identical, except that instead of an addition here, oh, you folks can't see that at all. Thank you. Remind myself of pointing that out. Okay. So we apply the formula with the negative betas. Cosine is even, so the negative sign disappears. The sine function is odd, so the negative sign comes out front, and then adding a negative is the same as subtracting. So this gives us the formula for a subtraction of two angles. And you can see that it's basically the same formula, except that we have a subtraction in the middle, not an addition like before. So that establishes both of our formulas for sine. We can add the two angles, we can subtract the angles. We can also use a similar trick for cosine formula. So give myself a little bit more space here. So cosine formula we want to know what can we say about the cosine of alpha plus beta. Well, let me make sure you can see that. What can we say about cosine of alpha plus beta? Well, we could do a geometric proof, draw a similar diagram to the one that we drew and go through all of those steps. But it turns out that we can just turn the cosine into a sine and use that. So we have our original identities that we proved with transformations. And one of them was that cosine theta equals sine of 90 minus theta. And so we're going to use that. We're going to take cosine of an angle is equal to sine of 90 minus that angle. So here we have cosine of an angle. That angle is alpha plus beta. And we're going to make that into sine of 90 degrees minus that angle, which is alpha plus beta. So we've applied that. Now we're going to group the sine a little differently. So sine 90 degrees minus alpha. We're going to apply the negative to the alpha. We're going to group that, and then distributivity, we also have to apply the negative to the beta. And there we go. So I've just grouped the bracketing a little differently here and done the distributivity. All right, so we have that, and now we're ready to just apply this formula. So we're going to get sine of the first one, in this case 90 degrees minus alpha, cosine of the second one, so cosine of beta, minus, because it's a subtraction, sine of beta, and then cosine of the first one, which is 90 minus alpha. All right, and now we're almost done. The only thing that we need to do is, again, use those parity identities. So we know sine 90 minus theta equals cos theta, and we know cos 90, or pi by 2 in radians, minus theta is sine of theta. And so we can deal with that here. Sine 90 minus alpha, that's just going to be cos alpha. Cos beta we're going to keep. Sine beta we're going to keep. And then cos of 90 minus alpha is just going to become sine alpha using those same identities. And typically when we write this, we'll reverse the order of these two in the multiplication. It doesn't really matter, but usually we'll write cos alpha, cos beta, minus sine alpha, sine beta. Okay, so that's lots of stuff going on. I'm not going to prove any of the rest of the things, but if you take two of these formulas, so let's say you take we wanted to know what tan of alpha plus beta is. Well, we have an identity that tan is sine over cos, so we can go sine of alpha plus beta divided by cosine of alpha plus beta, and then apply the sine and cosine formulas and chug through a whole bunch of algebra to get the formula for tan as well. So these are all options for us as we go through. I'm not going to go through and show you proofs and all the algebra for all of them, but I do want you to know how we go through and get them. So we're just applying the ones that we already have and using the algebra from there. And so the final formula for tan, once we work through all that algebra, is going to be tan of alpha plus tan of beta divided by 1 minus tan alpha tan beta. And just like with sine, we can get cosine and tangent formulas for a subtraction by just doing alpha plus negative beta and grinding through the algebra on that. So those are available. And what you'll find in both cases is that all that it does is change the sign in the formula. So if we're doing cosine alpha minus beta, it's this same formula, but with a plus here instead of a minus. If we're doing tangent of alpha minus beta, it's this same formula, but the plus changes to a minus and the minus changes to a plus. So it just reverses the signs in the final formula if we reverse the sign in the original. Okay, I'll give you a few seconds to think that through, ask any questions that you have. Hopefully I've adjusted there, Rumaisa, so that you can see what's going on. And then we'll start applying these, so showing you how you can use these to do calculations. Okay, so moving into how do we use these to do calculations, and this part is a lot easier than the proofs, so hopefully you'll find that it's a bit more straightforward. If you switch over to the document called Compound Angle Formulas, it's a PDF that was shared in the classroom, we're going to do some of the questions from that document together. All right. So if you look in that document, scroll down to the second page. Actually, I guess, yeah, second page. Question A asks us, what is the cosine of 5 pi by 12? And you might be looking at this going, wait a minute, we just did a bunch of formulas for adding and subtracting angles. There's no addition or subtraction in this. Why are we doing this one? And you might also be looking at it going, okay, like pi by 2, pi by 4, pi by 6, pi by 3. I can do all of those angles because that's just the same thing as 30 degrees, 60 degrees, 45 degrees, 90 degrees. And we know the exact values for those in degrees. But 5 pi by 12 is not a nice angle in degrees. So how are we going to do this? Well, we're going to play the main trick that we play with this stuff, which is we're going to see if we can get 5 pi by 12 by splitting it up into two different angles that we do know exact sines and cosines for. And so in this case, we're going to go with 3 pi by 12 plus 2 pi by 12. Because if we add those two things together, they have a common denominator. So we just add the numerators and we'll get 5 pi. And now that we've split it up this way, you can see we are getting a sum inside the cosine. This is also useful to us, and I didn't just pick these at random. 3 over 12 in lowest terms is a quarter. So we're going to get 1 pi by 4 is the same as 3 pi by 12. And here, 2 over 12 in lowest terms is 1 over 6. So we're going to get pi by 6 as the representation in lowest terms of that fraction. And that's really helpful to us because pi by 4 is 45 degrees, pi by 6 is 30 degrees, and so we do know exact values for these. So the next thing that we need to do is just apply our compound angle formula. Oh, that looks like it's getting a little fuzzy. Let me see if I can autofocus there. There we go. All right. So now we can apply the compound angle formula. So for cosine, it's cosine of the first times cosine of the second minus sine of the first times sine of the second. And each of these individual ratios, we know the value. So cosine pi by 4 is 1 over root 2, or depending on who you had as a teacher last year, maybe root 2 over 2 is your preferred way to write it. Cosine of pi by 6, well, that's 30 degrees. Cosine of 30 degrees is root 3 over 2. Sine of pi by 4 is also root 2 over 2. That's 45 degrees. And sine of pi by 6 is 1/2. Sine of 30 degrees is 1/2. So each of these ratios we know an exact value for, and now we can just multiply this through. Root 2 times root 3 is root 6. 2 times 2 is 4. Root 2 times 1 is root 2. 2 times 2 is 4. There's a common denominator there, so we can say root 6 minus root 2 over 4. And of course, if we wanted a decimal, we could just plug that into a calculator and get an answer. So this question shows you the power of these formulas. Before, we had exact values for sine, cosine, and tangent of 30 degrees, 45 degrees, 60 degrees, 90 degrees, and multiples of those. Now we can break it down a little further, and anything that's a multiple of 15 degrees, we can actually break things down and get an exact value of cosine and sine just using these sums and differences. So I'll pause there for a second. If you have questions, please jump in and ask them. Okay. So finally, we're going to take a look at least one more question from maybe two more questions from the PDF here. I don't want to take up too much of your time. I want to make sure we're done by noon, but I do want to show you two more. So we'll take a look at B, which is cos pi by 2 plus theta. And as usual, we're just going to apply the formula. So cosine of a sum is cosine of the first times cosine of the second minus sine of the first times sine of the second. And if we apply this, cosine of 90 degrees, if we remember from our graph, cosine starts at 1 and it goes down to 0, and that's at 90 degrees or pi by 2 radians. So cosine of pi by 2 is 0. That's that spot on the graph. Cosine of theta, well, we don't know what theta is, so that's just cosine theta. Sine pi by 2, well, the sine graph starts at 0 and goes up, and it hits 1 at pi by 2. So that's 1. Sine of 90 degrees is 1, and then times sine theta. 0 times anything is 0, minus 1 times sine theta is sine theta, and that simplifies to negative sine theta. And so we can see that this formula also helps us with identities, because now we've established the identity that cos pi by 2 plus theta equals negative sine theta using this formula. And if you look at the trigonometric toolbox handout that was in the classroom, you can see in the second row there, it says related angle with cast, and there's a bunch of identities. Oh, no, they don't have the pi by 2. Sorry, they have pi identities. So all of the identities in that second row, we could establish exactly using this method. Instead of pi by 2, you might have pi. Instead of theta, you might use minus theta, or maybe you use 2 pi. But anything of this form, we can quickly establish an identity for by using these formulas. Okay, can I move the screen down though? Yes, thank you. All right, sorry about that, Caitlin. Okay, Rumaisa, because it said in the formula that we add for QA, I'm not sure. Rumaisa, if you can give me a little bit more information about what you are wondering there, that would be really helpful. If we look at question A here, I chose to make an addition. There's probably another way that I could have split this up and used a subtraction instead. Let me see if I can figure out one of those. Yeah, so I could have done this as 8 pi by 12 minus 3 pi by 12 and done it with the subtraction, and then I would have had to use the subtraction formula. And I would have ended up with the same answer in the end, but I could have done it using the subtraction formula. 8 over 12 in lowest terms is 2/3. So this would be 2 pi by 3, which we have already done calculations for in a previous lesson. And then 3 over 12 is 1/4, so this would be pi by 4, which we actually used in this one here. Rumaisa, does that explain what you were wondering? Okay. So I'm going to do the last one here. We're again in the compound angle formulas PDF, and we've done A and B. I'm going to leave C and D for you to try on your own. I just wanted to look at A under simplify, so that the next one as our very last thing together here. So we have cosine 7 pi by 12 times cosine 5 pi by 12 minus sine of 7 pi by 12 times sine of 5 pi by 12. So we want an exact value for this. You'll notice there's no variables. We have the values for each angles. This is going to be a long haul through if we're going to try and evaluate each of these separately, because we'd have to, further up here, we found cosine 5 pi by 12 from the previous question A. That's this piece here. We can use that and do a very similar thing to get cosine 7 pi by 12, sine 7 pi by 12, sine 5 pi by 12. But it's not a huge amount of work, but it's a reasonable amount of work to get each of those. So we have a really nice shortcut, which is we can recognize, hey, wait a minute, this formula is the double angle formula, right? Cosine of an angle times cosine of another angle minus sine of the first times sine of the second. That is literally the cosine formula for 7 pi by 12 plus 5 pi by 12. So we're using the formula in the opposite direction than we did before. Before we would start with this and use the formula to get to that. Now we're starting here and using the formula to get to here. But this makes life really much easier. They're both the same denominator. 7 plus 5 is 12. So this is just cosine 12 pi by 12. And that is just cosine of pi. Pi is 180 degrees. So if we look at the graph here for cosine and we go out to 180 degrees, it's going to be down at -1. And so this is just -1. As you can see, that was a much faster way to evaluate this expression than figuring out each of these individually and then multiplying them together and then doing the subtraction. So hopefully that gives you some hints of how this is going to work. As you're going through and trying the questions, and I would ask you to finish the questions in the compound angle formulas piece. So as you're going through and finishing those questions, feel free to ask me anything that you'd like. You can drop me an email or you can do it through the Google Classroom. There's some complicated stuff in here. This is actually one of the hardest lessons of the course. So please don't feel like if something's not making sense to you, that means that you have some kind of problem. That's not the case. This is complicated stuff. The first time through, it shouldn't make sense. And if you have questions, please, please, please let me know. I'm very happy to help you out as best I can. All right, I'll stick around for another minute or two. If you have questions about this or about any of the previous stuff that we did, you're welcome to ask them here. If you're the second last or third last person to leave the stream, if you wouldn't mind just leaving it open until the last person has got their question answered. If I drop down to just one student in the stream, I have to shut the stream down. So if you can help that last person out by just leaving the stream open, you don't have to be staying and watching it, just leaving it open on your computer is fine. All right, thanks a lot, folks. Okay, it doesn't look like anyone has questions. So I'm going to give it another 10 seconds and then end the stream. If you're typing something longer, just copy it, put the word question in, and I'll make sure that I stay on until it's answered. You're welcome, Daniela. Have a good rest of your day. All right, take care, folks.